All right, so today's a little different. I usually do record this lab so that you can look back and do observations on the glass at a later time. Sometimes the glass does have some instabilities and there'll be some breakage, and so this allows you to see what happened, instant replay style. As a result, I've got a microphone I'm going to be putting on so captures what I'm saying, obviously. Looks like that is active, so we'll play along. So a lot of observations to be made today. It'll take me a moment to get this projected on screen, but basically the glass compositions that we prepared last week are currently baking out here at 1,150 Celsius, which is over 2,000 Fahrenheit. So a lot of radiant heat there. Looks like there's not any cracked crucibles, so that's good news. We, in the past, poured right at 1150, but I was noticing a couple years ago, that it was a little bit more viscous than it used to be. And so I think my thermocouple on this guy was off a little bit, and so I've started bumping it up to 1200 in the last half hour so that it'll be a little bit more easy to pour. So what I want to do next is just kind of calibrate our observations here. So let me get that on screen. So there's going to be several things we're going to accomplish. So first thing we'll do is talk about what to look for. Then I'll have to get a few volunteers to do several different activities as we're making the glass, such as some torch work, help with the door, help stamping the glass with the composition letter, being ready with a fire extinguisher. Never had issues with this particular lab, but that doesn't mean it can't happen. Hot glass like this, if it just brushes your clothing, it catches it on fire. Or my clothing, whatever. So, and then finally somebody to keep me coordinated. And so with the pick list and the batch list, there's 5 jobs there. Think about which one you want to add to your resume there. After we pour all the glass, we will then have to wait because it starts off at hundreds and hundreds of degrees. And so during that time, we're going to look at a art glass type video. It's kind of cool to see how that works. Then a video on making bottles, how it's made video. Then I will give you some instructions on cardinal glass next week. And so during that time, I'll pass around this sheet. Make sure you sign this sheet on the back. This is your ticket to cardinal glass. And they do check and they do hunt you down. It's kind of part of their legal obligations. And so make sure you sign this so they don't have to cross-reference and see who didn't sign next week. So I'll give you some instructions on that. And then finally, we'll be able to do some observations of the glass. You might be asking, well, what exactly does observations of the glass mean? Well, for one, you can measure the diameter of the glass and get physical properties of the glass, but there's additional things that you can do during the process. Remember the story from last week. We have a glass former, silica, that has been fluxed with sodium carbonate, which turns into sodium oxide in the furnace, and fluxed and stabilized with calcium carbonate, which turns into calcium oxide in the furnace. And that makes this broken up network solid that can't crystallize. Normally it's clear and colorless. By adding transition metals, we're going to impart a color, lots of blues and greens, and unfortunately not a lot of reds. Red's difficult. But we'll have a sampling of a variety of different colors, purples, dark greens, brighter blues. So that'll be interesting to see. So obviously that's part of the observation. And if there's a question on the lab, there is, about what happens in the furnace to the sodium carbonate and calcium carbonate, this is it. You know, it's nothing too profound. It's just this vibrates thermally until this eliminates a CO2 from the CO3, leaving one oxygen left. So this is the conversion of a carbonate to an oxide. And that happens at around 800 or 900. And then it's this material that melts and does the actual fluxing. And so remember, this is a flux, and calcium's a flux stabilizer that causes some bridging. Now, when we're pouring the glass, you'll notice some different viscosities. All glass can be described by a curve that looks something like this. So calibrate your brain here. This would be a lead oxide glass because it's got a much lower range. It's a lot easier to melt lead oxide instead of silicon dioxide. But regardless, there'd be a similar curve for the silica glass that we're making. So what's being shown here? Well, we've got log viscosity, and so this is basically a solid. And as you heat up a glass, it kind of softens to a point that at some point it becomes easy to flow under gravity. You can pour it. Depending on the composition, this curve changes for each glass. So let's say, for instance, instead of a lead oxide glass, I had a silica glass with low flux. Well, with low flux, it might have its curve all the way up here, and this might be all the way up to 1200 or 1300 degrees. Imagine this curve, imagine this plot is much, much larger. As I add flux, what that does is take this profile in viscosity and temperature, and it starts migrating it downward. But there's limits to how much you can go with a silica glass. Now, we also added some borax and also some Gerstley borate. Well, that's altering the glass former composition and also moving it to a lower, easier to melt material. Now, what we're doing is choosing a temperature, 1200 degrees, and then pouring glass A, B, C, D, E, F, G. And so we'll notice some different viscosities because each one has its own curve, which would have a slightly different viscosity at 1200 degrees, which is our pouring temperature. And so that's what's going on in the background, and why we'll see some that pour out into a smaller little hockey puck and others that are going to pancake out and get somewhat bigger. You know, some years it's a fairly subtle difference. We're pushing it a little bit more than normal this time with a few of our borate batches, and so I'm not really sure how big these are going to get. Hopefully it's not going to get, you know, crazy water glass going everywhere. Probably not. But we'll be keeping an eye on that, and that's how to describe what's going on. The temperature viscosity curve is variable depending upon composition. Now, how do you know where you're at in viscosity? Well, we're going to have to do that qualitatively and semi-quantitatively. If you look at what the glass does as it's being poured, through the years, I've kind of tried to keep the timing and motions identical as possible. So what you will notice is that I'll take those tongs and I do the pouring because it'd be pretty easy to get hurt. So I'm trying to kind of limit the possible things that could go sideways here. So a lot of observation, and like I said, there will be some different roles, but I'm going to be putting myself in the furnace. And it is enough that it would catch your clothing on fire, so I have to wear a shiny suit it's stylish. And some fairly hefty gloves to make sure. And you'll notice the gloves will be smoking or steaming, one of the two, off-gassing something. But as I'm pouring that onto the slab, which the technical term apparently is the marver in the glass world, if you see a thin bead and an easy pour that spreads, it's a low viscosity. Obviously, thicker, medium. If you see a really thick pour, that's telling you that it's not able to draw into a bead, and so it often stands up taller and doesn't spread as much. And so these are some visual cues that you can use to benchmark relative viscosity. And you could call it low, medium, high. You could rank it 1 to 5. You could rank it 1 to 10. There'll be an instant replay on camera that you can look at later on the playlist. It's up to you. But try to get an assessment of how the ingredients we chose cause different viscosities. Now, that's not the only clue, because if you like to get all the ingredients on there too. If you compare some different glass samples from the past, you can see some differences here. So this is comparing the molar flux amount. Notice the silica is the same. The flux changes. The calcium stabilizer flux is the same. So this is only due to a change in sodium content. And you can see a change in diameter. Clearly, there's a quantitative way to look at the implication of viscosity, but this is an indirect way of measuring it. You know, distance, diameter isn't viscosity, but it's a consequence. If the viscosity is low, it's able to pour out and flatten easier under gravity, and so larger disc correlates to lower viscosity. Smaller disc correlates with higher viscosity under certain assumptions. And the assumptions are the temperatures are the same, and the pouring rates and the time it takes me to get over there is the same. And so assuming that the temperature and the timing of the pour are the same, then this scales directly with viscosity. So that's a way that we can assess what's going on with viscosity. There are some questions in the lab about alternate fluxes. I stopped doing that. So we're going to have to use these pictures as our indicators. Why would I stop doing that? Well, because we're pouring at 11 to 1200 Celsius, it's not a high enough temperature to get potassium glass to behave correctly. So what happens is you pour this stuff out, and it looks like, in some cases, this giant Hershey's Kiss, and they always explode and shatter all over the place and send glass shards. Not quite in a radial, not quite in a full, like, spherical pattern, which would be bad for us. When it shatters outward and down, and so you may get hit by glass chunks if you're standing up here, but if you wear your goggles, you'll be fine. They're not super high velocity glass chunks, and they typically more like crack and spall off the sides instead of like grenade. So, but these, they're unstable. Too tight of a glass because the potassium flux is not as effective at this temperature at making a easy to pour glass. We've been talking about sodium, and it's kind of the middle of the ground control. Lithium, the problem with that is that lithium is so reactive. What I was getting with this one is the lithium flux can actually evaporate, and it actually softens the brick, and you kind of flux the interior of your furnace unintentionally because lithium is really light. You know, look at it up there, number 3. And so, although it's wildly effective at fluxing the glass and making it just pour out with very low viscosity, it's kind of damaging if you're not set up for just using lithium. In theory, for the lithium flux, I would probably be best to pour at around 900 or 1,000 degrees. But since we're kind of all doing these batch-to-batch comparisons, I'm not tailoring to their respective pouring temperatures because it's all kind of tailored to sodium. So anyway, I'd have to go to a lower temperature range for this, higher temperature range. If you pour them all at 1150, this is what you get. And so the smaller the ion that's a +1 charge, the more rapidly it can move. And in theory, you could say the more it disrupts the silica bonds per atom, per ion. And so that higher effectiveness leads to a lower viscosity because it is a more effective flux. You can kind of think of it like a basketball player, you know. Sometimes there's people that are a little smaller than others and you might discount them, be like, oh, they're not tall enough or whatever. But sometimes they're the fastest ones out there that can actually get to a position way quicker. And so it's like they're in more places than one. And so then let's imagine you get some football player playing basketball. It's kind of a, you know, bigger guy. That's like potassium, that they're an athlete, but they're not quite as fast. And so in that case, they're not as seemingly many places as at one time. And so this is only really a mass diameter argument because they're all +1s. But this one moves faster at a given temperature because it's smaller. It's physics, you know. Same kinetic energy, smaller stuff moves faster than larger stuff. At any rate, that's the discussion between the alkali metals, lithium, sodium, potassium, and the way they relatively, the different ways that they flux glass. So that is the relevant theoretical stuff. And so obviously you're going to put your details, and then you have the details for the whole group. Now, some of these are going to be easy. Like I said, we don't do sodium flux anymore, or we don't do lithium potassium anymore, so these are all sodium. Benchmark viscosity, measure the diameter. A couple of them may break, and so I'm going to record that. But then, remember the Alamo, remember this spreadsheet that we made last week. So this already has all the ingredients. You have access to this. I'll be working off your pick list here, and you can take these back when we're all actually, I'll probably scan those before you take them back as well, but we've got it mostly recorded here. But we've got our batch, we've got our colorant, but then over here, the area that you're not messing with, you'll get the concentration, molar or percent, weight percent concentration of the ion over the fired glass batch. You notice that this starts off at 165, but it loses carbon dioxide. And in some cases, it loses some water. And so the mass goes down. And so this is the theoretical weight of all the glass we produce. And we don't recover all of it from the crucible. But that's the weight that we would expect this amount of iron oxide to distribute on. So if you take this amount of iron oxide, decimal percent metal oxide, or metal and oxide. So that means that this is 0.699% or 0.699 times 4.98 tells you just the iron content of the oxide. And the rest is oxygen. But you would take this number times that and distribute it, divide it by that batch weight, and then you get the, come on, cursor, table over here that shows the final concentration in the glass, which is 2.6%. So the glass that we see will have a color density that would be scalable with a 2.6% iron in the batch, or a 0.087, 0.137 chrome copper. This is the table you can use to answer those questions on metal ion identity and percent concentration. So remember, this is already in true percent over batch. Make sense? This facilitates, this is the first year we've done this as an online spreadsheet, and it looks to greatly simplify this process of shuffling around spreadsheets and which one do I use. And so I think I'll continue doing that moving forward, but don't forget that that's available to answer your questions on the lab. And so that will get you your concentration, weight, and ion. And if the ion is more than one, you just put a comma, you know, like let's say with that example with copper chrome. The ion, Cu2 plus, comma, whatever, Cr3 plus, or Cr2 plus. And then you would just put the copper weight, and maybe put copper, you know, 0.076 Cu, comma, 0.0 blah, 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 chrome. Whatever, use the space, just list whatever's there. If there's 5 different colorants, write small, you know, whatever. And then some of those other questions, and finally a few other videos. Some of you are familiar with Smarter Every Day YouTube channel. He did this whole expose on internal stresses in glass. We'll talk more about that after we pour the glass. I've got a light table and some polarizing films that we'll be able to use to see the stress in the glass that we pour. We are doing a process called quenching the glass from furnace to steel plate. And as a result, it's really hard, but there's really high internal stress. If you're gonna sell these items, you know, whatever, craft, stabilized glass, you would have to take the glass and then put it overnight in an annealing oven, lower than the melt point, but above the annealing temperature, and then it relieves the stress and makes it no longer likely to explode. Crack, shatter. Shatter is a better word than explode. But the internal stress is kind of cool to see. So we'll be looking at that internal stress field. I'll show you how to do that here in about, I don't know, 45 minutes, an hour once we're ready. But that's all the stuff you'd be turned in. Then this gets turned in next week. What would you rather do? Would you rather have this be due next week on the field trip day or the following week? Following week, probably. Later's better. Okay, yeah, it doesn't really make a big difference to me since there's no lab next week. So we'll make this be due in 2 weeks, but the danger there is it makes it distant history. And so complete as much as you can early when it's fresh in your mind. I can't overstress that's true now, it's true in your future career. When you're writing a report on something that happened a year ago, your report's going to stink. I'm sorry. So keep good notes and try to get as much of that detail captured when it's right there in mind. It takes less time, it's easier, trust me. So try to work with that in mind. All right, so I think that's the main stuff to discuss. So then let's talk a little bit about the logistics here. We've got jobs. So the first job that I will need some assistance with is the door, actually. So Let me rearrange the old camera here. Come on, you can do it. I believe in you. Well, encouragement goes a long way with electronic devices sometimes. So for this one, I'll need somebody to probably wear a set of those heat gloves. It's not terrible, but you'll just grab here, and I'll be addressing the furnace this way, so you'll just want to pull up and out. I grab the crucible. After I'm convincingly pulled that out, you then slowly move it down. Now the problem with this job is that this is a metal door that's on this kind of a hinge that moves like this, and it's got refractory brick, which is really brittle, and at 1200 Celsius. And so in the event that you jar that, chunks of that could fall off and unleash some mayhem here. And so it's a slow up, and then pause, and then slow down, and then always be careful when you engage the bottom and top of the arc. So, does anybody want to do the door job here? Any volunteers? All right, thank you. Thanks. That's a gas cylinder for Thursday lab. I'll be moving in later on. Different class. So anyway, that's the door. Next up is the torch. So if you've maybe had some experience with soldering, plumbing, or just like using torches, this one is a little bit hesitant to light sometimes. So obviously turn it to on, and then you pull slowly. And if you pull too quick, it has a habit of not lighting. And so it's a slow pull, so it's gas, and then there's a piezo spark that, I don't know if it needs to get cleaned out or what, but just a little slower than it used to be. I know how it feels. So that's the way to do that. Now, as I'm pouring the glass, the crucible will be about this far off of the surface. And what you'll want to do with this is bring the tip of the torch to within about an inch of the glass, so that those bright inner blue jets are the hottest part. And so that is what you're going to be using to heat the string of glass exiting the crucible. The reason for that is that at the end of the pour, I'm going to be removing the crucible, and I want it to pull free from the glass without making this giant string. If there wasn't any torch, I'd pull away, and there'd be this giant string like fishing line, and as it gets harder and harder, eventually it starts dragging the puck of glass across the table, and it just unleashes mayhem. So this fixes that, because the glass is least viscous at the hottest point, and so it breaks free, and then as I'm messing around over here parking the crucible and trying to prevent people from getting impaled with fiberglass strands, you then take the torch and you fire polish the glass. So that just entails using the inner part of the flame and just dance it all around the surface, especially where the glass pulls free. It's kind of like a navel, you know, a little defect in the glass. And so you kind of polish that, and it pulls it down into the glass, and you'll end up with a nice flat disc. So any takers for the torch work? High stakes, high pressure. Want to do it? Okay. So thank you for that. Now also, this job is probably the most hazardous, because I'll eventually have hot crucibles here, and you know, you have to keep track of all that. And so typically this one uses a latex glove. The big fire gloves, it's hard to maneuver this, but the radiant heat, it's actually, you might think, oh, it's nothing. It is something. You end up with red, it's pretty amazing. So I've found that just using a rubber glove knocks down on that radiant heat, and we'll fine tune that as necessary. But we've got those orange gloves as well, so it depends on your preference. Next up is the stamp. This one also gets you up close and personal. So compositions this year consist of a 3 and a letter. So the 3 die will stay constant, and our first batch is 3A. I recommend this job also wear a latex glove, or actually it's a nitrile glove, to knock down on radiant heat, because you'll set up the dies upside down and backwards. Now, the problem with that is that it's really common to get them in the wrong orientation. So the way to test for that is you just kind of gently press that into your skin. You know, don't like push it through your finger or anything, but it leaves a little momentary mark, and that makes a way that you can verify that you've got it oriented properly. So that says 3A. I'm sure of it now. Once you get that straight, it's easier to not make a mistake. But you'll hold those 2 dies now that they're properly oriented. And when it's time to stamp, that'll be about 5 to 10 seconds after the torch work is done. If this is the glass disc, you just kind of move in and push it into the lower, kind of like lower middle, about a centimeter from the edge. And that way it puts an impression, it makes a good impression in the glass, and makes it so after it cools, we can tell which batch it was. So anybody want to do the stamp? Stamp? Okay. It's kind of an interesting job. It definitely can get kind of hot. So, but once we figure out the sequence, everything usually goes pretty smooth. The next job is, and you don't have to like, I had a guy one year that volunteered for this one, and as soon as the door opened, he, no joke, went like this, and he was like ready to go, you know. You don't have to be quite that ready. I'm not trying to like belittle it. He was taking it seriously, but it can just sit there. We'll have a few seconds, but let's imagine that I pull the crucible out and something odd happens and it cracks, and let's say chunks of ceramic fall on my shoes or whatever and ignite my pants on fire. You know, the Dr. Ray, liar, liar, pants on fire. That's a great time to have the fire extinguisher. You know, I can stop, drop, and roll and use a fire blanket and do demonstrations for you, but you know, just killing it early would be great. Now, in the event that this one fails, because I haven't recharged that for a long time, but there is one out in the hall as well. I'm a fan of fire extinguishers. We used to have a lot more in labs, but OSHA changed rules and said, as long as you're within 50 feet of a fire extinguisher, or whatever the number is, then you don't have to have any more. It cuts down on fire extinguisher checks. Besides, we don't want people fighting fires in a public building. We want them safely and calmly exiting the building. And I always push back by like, well, what if the fire is blocking the exit? We don't want you to fight the fire. We want you to safely and calmly exit the building. What if I'm on fire? We don't want you to fight the fire. We want you to safely and calmly exit the building, because we can't give fire safety training, because then we'd be liable for certifying fire safety training. So we just want you to safely and calmly. So it's like a broken record. You know what fire safety training and fire extinguisher training is? It's the word pass. You ever had this? Pass. I'm not going to squeeze this, but P, pull the pin. A, aim at the base of the flame. Not the flame itself, the base of the flame. You got it so far? The next one is squeeze. And sweep side to side. PASS, pull, aim, squeeze, sweep. There you go. Fire extinguisher safety training. Now, normally this also involves building a fire somewhere out in like a parking lot or whatever, campground, who knows. And then people take turns dousing it with a fire extinguisher. So we're going to skip that part. But this is a universal, it's a CO2, so it would work great on this. But that's, so anybody want to be the fire person that just stands there just in case stuff goes sideways? All right, thanks. Like I said, this is probably the 13th year. That's a good point. That's a good point. I'm not superstitious. We'll be fine. But yeah, I guess I did just announce that, didn't I? I should have waited till next year, right? Last year was the third. Well, anyway, we've never had a problem before. So then finally, the job we call the MC. There is no records to spin or anything, unfortunately. But this job just keeps everything coordinated as I'm pulling stuff and referencing batches and maybe highlighting what to look for. So anybody want to be kind of like hanging around here coordinating with my batch diagram as I pull stuff out of the furnace? The MC. Anybody? Anybody? You'll love it. It's great. No takers. It's a very helpful group. Really appreciate that. Nobody? Well, I'll just have to draft somebody that's standing up here. Now watch, there'll be this giant gap right here. Everyone's gonna be like lined up at the back of the room. Well, okay, appreciate that. Appreciate that. Public shaming. Wow, charity is dead. All these non-for-profits are gonna go out of existence. This is amazing. Anyway, you know, there's time to learn. So, well, let me shuffle these into the right orientation quick, and then we will proceed. So I do recommend, well, you have to, wear your goggles. And there'll need to be a little bit of a zone here to be clear, but you know, you can bring your chairs forward, you can stand around here. Really anything within a radius of about 6 feet may get a little bit of glass. If we have one that breaks, the way that it breaks is the disc shatters out, and so the trajectory is about like this as little glass chunks rain down on the floor. I have had them rain into my pocket before. It's about the right height. But that's about the likely most hazardous thing that could happen. But yeah, feel free to get where you can see. And we will proceed. So, as I said, I have to wear a heat-resistant suit. Also have to adjust the camera a little bit so it's pointed at the plate. Yeah, it's pretty much right where it was. Right around that corner is about perfect. So it's kind of unusual to have a foundry suit with a lapel microphone, but you know, that's the way we roll here. So then, that's a calculator. I need to readjust the camera to the plate here, so. So that's probably pretty good right there. Because most of our business is going to happen right here on this first plate, and that's really for stacking crucibles back there. So I think we're in good shape there. So let me grab my gloves. All right, so if you want to go ahead and test out the torch, make sure that makes sense to you. It's a slow pull. You can feel it engage the clicker. Yep. And like I said, it's closer than you expect, but just not touching the glass, but getting pretty close. Um, and then if you wanted to stand like right here, that's like perfect, so I can still kind of see what's going on here. So 3A, this first one is beach sand, so that's the stuff from Lake Michigan. We got 9 grams of borax, sodium carbonate, calcium carbonate. It looks like a little bit on the low side for the calcium flux. Is that really 5 grams? So was it 5 or was it 24? Well, I mean, the calcium carbonate, anyway, it might just be mislabeled here. Oh, I see, calcium carbonate limestone. Gotcha. Perfect. So this one has 19 limestone and then 5 of the purified. I didn't read the next line, sorry. And this is iron, so this is the one we've been talking about. So we're expecting kind of a green glass. So we'll pour that one about right there. Now this one has borax in it too, right? Borax? So this one might be a little runny, so might be interesting. So if you want to go ahead and carefully open this. All right, now start fire polishing the surface there. Try to get that to pull in. Looks good. So now you can go ahead and move and stamp the. That can be more straight down. There you go. That'll work. And usually just a little bit further in toward the middle, but that should be fine. 3A. So that one actually spreads out. I could tell it was a little different on the borax. And at the moment, that looks really dark, like brownish color, kind of interestingly. There's a term in the glass world, it's called the striking temperature. It's the temperature at which the final color of the glass fades in. And what's interesting is it's temperature dependent. So you'll actually see the color of some of these glasses change a little bit. But this looks a little different than normal straight iron I've seen. I think it might be the borax, or maybe it will eventually fade to green. You can also kind of tell the top edge cools faster on the crucibles and acts more like a glaze. And so you can kind of see the eventual color first here, and then it kind of matures in the glass. So that one is 3A. So next up, oh, you already did that, thanks. We've got silica. This one has some alumina. Fairly standard. We got sodium carbonate, calcium carbonate, a little bit of dolomite. So it's basically a standard. Well, it's got alumina though. So this will be a little bit of a smaller viscosity probably, or a higher viscosity, smaller disc. And there'll be a copper iron. That's a interesting mix, and I'm pulling from the left, right? Yeah. 3B. 3B. Okay, let's go ahead. So pull again. You want to restart that? There you go. And a little closer. There we go. Really focus on that middle part there, get that to sink down in as much as possible. I think that's good. So we can go ahead and move in and stamp. Yeah. When you do the stamp, it's good to try to choose a direction that doesn't have you over the hot glass. It might catch your sleeve or something, so be careful with that. But yeah, this will be a nice bluish, blue green maybe. We'll see. And I think this is going to persist as a darker color on that iron. That's a little bit of a weird. Not weird, it's different than normal. I think it must be the borax. Another interesting effect that we're seeing on this copper is that the carbon monoxide from the flame actually did some reduction on the surface film of the glass. And so you see some copper particles that makes a bit of a copper shine on the top that if you look through the glass, you won't even see. It just looks blue. But in reflection, you can actually see this nice copper pattern on the top. So that's kind of cool. There's also some little flakes in there. That's got me concerned. The aluminum may not have completely melted out. That means this one might shatter eventually. So let me grab a ruler quick. Anything that's interior in the glass, like really large bubbles or inclusions, have a way of messing things up. So this one is approximately 65 millimeters that direction and 62 the other direction, just in case. So
does that mean that we maybe didn't grind ours up enough?
You know,
or is it just kind of one of those things?
it looks like the aluminum, if this is what I think I'm seeing, the aluminum may have been a little bit clumped. And so in that case, yeah, milling the aluminum a little bit, but you can actually see some chunks of something. Right, so that sound, well, no. That always happens with every glass. And the reason for that is the shrink coefficients and expansion coefficients are different for the crucible and the glass. So as this is cooling down, and we study coefficient of thermal expansion, right? That's what's at play here. As the glass solidifies, it no longer is flexible and can't match the rate of shrink to the crucible since they're different. So what you're hearing is called crazing of the glass. And every time you hear that sound, there's a little crack that forms in the layer of glass on the side. And if you stand and look at the glass, you can actually see it crack with that sound. And so, like looking right down the top right now, I can see cracks forming with every sound. And that normally happens once it's down around, well, just below the annealing temperature actually. So 500 or 600 degrees or thereabouts. And so eventually there'll be a chorus of that sound from all these hot crucibles. So next up, I think I'll try to sneak this one in. Another strategy with this is always try to aim the flame so it's not hitting the previous glass. You can get hot spots that will cause cracking. So try to aim this way. When I'm doing this next row, try to aim away from this glass. So there's a lot of like strategizing on angle, but I'll put the next one here and I'd say try to aim it this way and give this one a little bit of breathing room. I think we've got 9, so let's try that. A little bit risky, a little close, but I'm a little on the edge. So we got some pure silica, U.S. pigment brand, sodium carbonate, calcium carbonate, maybe a little bit higher than normal on the calcium, maybe a little lower than normal on the sodium. And then this is a chrome copper. So should be interesting. So composition 3C, we'll put right there. We're pulling from the right, correct? Okay. Really hit that top part there, try to get it to sink in. Should be good there. Is it getting too toasty for you?
A little bit.
Yeah, if it gets too much, we can switch to a more insulated glove. You got to be careful with these stingers on here. I have seen some. Well, actually, I've done it myself. You like flex them, you're like, wow, fiberglass flexes, and then all of a sudden it breaks and stabs you in the finger when you least expect it. So it's dangerous because it's kind of flexible, but then it reaches a breaking point when you don't expect it. So I will eventually break all those off and make it so these crucibles aren't as hazardous as they are. But for now, just resist the urge to touch fiberglass. It's not exactly your friend. So, and this one as well. Ooh, yellow flag on the play. Now, interestingly, it doesn't look like they ended up in the glass. Well, we'll see. It looks good for now. So, and I've been fooled before. You know, it's not like a complete death sentence when you have inclusions, but it's a concern. So the good news is so far so good. So, but yeah, that one definitely was more reluctant to pour. It was a higher purity silica. Was that really? I don't know what I'm looking at then, because I thought this one was.
Well, we use the same distillery.
Yeah, this one's right. So.
This was composition C, right? So U.S. pigment, that wasn't sand, right?
No.
I mean, that's the white silica. So what is that black stuff?
I got nothing. That's everything that I put in there.
That's the right crucible, right?
Yeah.
Now that's weird, because if I were guessing, I would say that this one had sand in it, a coarse sand that for some reason didn't completely melt. That's really weird. I don't know what I'm looking at there. It's a mystery. There's something in there that is different than expected. So, but the color looks right. So, well, let's continue. So next up, we've got composition D. And so this is pure silica, presumably. 45 sodium, 20 calcium carbonate, 4 borax, 5 aluminum. That might kind of cancel out. The alumina tightens up, the borax cuts it down. I don't know what's going to happen, actually. That's kind of like a yin and a yang fighting each other there. And then it's a copper iron this time. But yeah, interesting combo there with the borax and the aluminum. So this is composition D. And I'd say angle this one this way. And if the heat starts to be a problem, we can switch to a orange glove if you want a thermal glove.
Yeah, I think that'll be best.
Really? Okay, well, just go over here in this drawer. We'll find a more aggressive thermal glove. The problem with these really thick ones are it's really hard to pull triggers. But that one's got a hole in it. One might be okay. Just watch out for the holes there. See if that doesn't cut down on the uncomfortability. Okay, so composition D. Pulling from the middle. Ooh, hold on a second. There we go. So definitely a bit thicker. I think the aluminum must be tightening that up quite a bit. Then work that down in. All right, I think that looks good. And so, yeah, at the moment, that's a really unusual color. It's kind of a, it starts off yellow and then flashes this kind of like a sea green, it looks like. Look really close, poke myself in the eye. It's like lemon or lime kind of at the moment. More chunks. What is going on with the chunks? What is going on with the chunks?
It's not just us. Yes.
Yeah, go for it.
Wow. That's a very cool color.
That's a really unusual color, yeah. We'll call out some measurements in case, and so we already got that one. So C, which is a kind of a dark green, we got 63 millimeters on the major axis and 54 on the minor. Yeah, I'd resist the urge. And so that was C, and then on D we've got 59 and 57. Oop, and I just melted a little bit of my ruler there. It happens. So, okay, interesting color. Hopefully it survives. So, next up is E.
You were aiming for red.
And so this is a silica beach sand, mason sand, and play sand. So if any have unmelted stuff, but it won't be this one. You know, this one has the most mix of unknown sands. 10 grams of borate plus 5 grams, or Gersley borate plus 5 grams of aluminum. So this one is going to have a high tendency to flatten out, but the aluminum makes it a wild card because you don't know how much is going to prevent that. Plus 10 grams of borate. This is a double borate. I don't even know what that's going to do. I think it's going to be pretty flat even with the aluminum. Anyway, so the color, oh, and we've also got 50 grams washing soda and then 10 grams limestone, 18 dolomite, and 0.17 manganese oxide. So this one should be purple, but there's so much going on with this, I don't really know what to think. See, look at the color. You see what it just changed into? Now it's no longer yellow, it's no longer lime green, now it's fading into a, you know, sky blue, robin egg blue color. So this is probably the final color. Well, we'll do the next one here. And so you'll probably want an angle that's about like this. And so is this going to be too, probably not too hot. So just be extra careful of these crucibles. Maybe I'll move them out of the way here. All right, get that out of arm's way there. And glass shards. So we're pulling from the left, and it's composition E, right? F. E. Okay, you already switched it. E. Composition E. it's really low viscosity. You'll want to restrike the flame. There you go. Focus on the surface some too. Look at how thin that little bead is. That's crazy. That's double borate, I guess. Look at that broke off. That is, yeah, that's ready to go. That's the lowest viscosity glass I think we've ever had. Red?
Well, it is.
Yeah. Yeah, that looks orangish right now. Well, of course it's glowing, so. I made orange glass. It's really elastic too. Look how it's like, nope, not letting go. There you go. So all that sand had no problem melting out. That borate moves it to a whole lower range. And so it's pretty similar, I guess, in diameter, but this one poured with such a thin bead. It's brownish now, so we'll see what we end up with. So I think we'll just try to do the 9 just like that, but might get kind of close. I think there's enough room there. So composition F, 90 grams Fisher silica, 5 grams alumina, 50 sodium carbonate, 20 dolomite, 0.2 chrome with 1 gram of sodium sulfate. So if there's going to be bubbles, there should be fewer bubbles with the sodium sulfate, but this is going to be a much tighter glass. And it's going to be green, probably. So, so that's what happens sometimes. So let's go ahead and put the chunks in a beaker. In theory, it could get, it's still pretty hot. Well, you never know, but that's a pretty typical shatter. The good news is the camera's rolling, so we can see how it shattered. But looks like we've got some dirt that's going to make it into this sample as well.
No one dusts in here.
Beaker glass I cut myself on.
Yeah, there was one time where you're like, "What's in this beaker?" And it's like shattered glass. And you're like, "I'm bleeding." Yeah, don't dig around in shattered glass beakers. That's a bad idea. So, does that look like every piece? Ah, yes. Little ricochet there. Looks like I need to clean my brush. All right, so there you go. We can still talk about the color. I should label that quick. So that was D, right?
Yeah, the impressions don't do much when it's shattered.
3D. It was good glass. So we'll set this over here for now. Next up, we've got 3F, right? And that's the one I was just calling out that should, in theory, be green. So I'm pulling from the right. So then, oh, it's getting crazy. All right, so let's watch the chunks there. Everyone should be getting a hazard pay today. You're not getting hurt by any of that, right? It's just bouncing off, right?
Yeah.
It's kind of an odd feeling, but so we'll have to pick up some more.
This one's tough. There's no way it makes.
This one's definitely blowing up.
There's a lot of chunks.
Look at how
in
many
it.
chunks.
What is going on with the chunks? I'm confused.
What kind of
It's like-
sand did you get?
I'm wondering if it's the alumina that's not melting out.
It's cool that you guys can see the copper on top too.
Yeah, I mean it's not a total loss. In theory, it could be melted back down, but
Probably weaker.
all right. So let's clean that one up. These are breaking earlier than normal.
Oh, okay.
Oh, good.
Normally, they break during the video phase.
So all I'm hearing is that we're overachievers.
Yeah, this is happening fast with you guys. I mean, we knew this was a possibility. So now the good news is it's kind of a cool color. Yeah, you know, that's Dr. Ray being an optimist, I guess. Any other large pieces? Aha. Well, that one went far. All right, so then I'll put the rest of the small stuff in the glass bin in just a moment, but oh, lost one. Okay, so this was B. Maybe I should just keep the Sharpie over here. The way things are going. 3B. It was good glass. Put them on display. All right. This is a camel hair brush, and so I've gotten to discover what flaming camel hair smells like before. I don't know. Must be interesting. They always use camel hair brushes for these types of brushes. I don't know. It's like boar bristle brush, that's a thing too, but those are coarse. Paint brushes can be that. I don't know if it's stamped on there, but okay, that is, I think, it. A little too much excitement today. So next up is composition G. 30 grams purified silica, 45 beach sand, 5 alumina. That alumina, I think that might be our issue. I'm gonna have to check that ingredient. Now the good news is there's 15 grams of borax, and so if there was something that could melt it out, that's it. 50 grams sodium carbonate, 10 grams crushed limestone, 10 dolomite, 0.6 copper, is that really, 0.05, 0.65? 0.65 copper, 0.05 manganese. A lot going on there. So, copper manganese should be kind of bluish purple. So we'll attempt to put this guy right here. And so I'm pulling from the middle. Okay. Here we go. 3G. Gloves are smoking. You want to strike again? That's not a full fire there. There we go. It's igniting on the hot glass.
Is the sound effect necessary?
It really was. I felt the need. I mean, it is mine, so.
Yeah, that makes sense.
Oh, this one's yours?
Bonded.
Yeah, so we got more copper effect going on there. It looks smooth and stable. That's a good sign. Yeah, like you're saying, I don't know about that little guy back there. It's like a little green football. Have I measured that one yet?
No.
Well then, better hurry up. So this one is,
I'm gonna blow up right now.
yeah, 56 millimeters on the major and 48 on the minor. Oh, it didn't blow up in Dr. Ray's face.
I think you need to remeasure just to be sure.
I don't know, Dr. Ray. That looked a little bit different to me. Well, this is at least a lot of variety this semester in viscosity. I mean, these are pretty dramatic differences in size. So this one's going to be a bit more of a challenge because you're going to be kind of curving back this way. And it's fine to do it from here. I'd probably recommend it so you're not reaching over the whole thing, but it's that angle right there. And put your hands a little close to these, so don't expect that one to shatter. That way you won't be surprised. And because of the uncertainties in life, we'll move that one down. So I'm pulling from back, left, and composition H. So North Shore sand, 85 grams. 4 of alumina. 50 grams sodium carbonate, 24 crushed limestone, 5 iron oxide. Now this one doesn't have borate, so if we see a lot of white chunks, that alumina is not our friend. Alumina's worked in the past, but I don't know, maybe, I don't know what's going on with it. It's a mislabeled container or what, but well, it's having a bad day. But so the iron oxide, 5 grams, in theory should be bluish, greenish, oh green. So we'll put that one here and hope for the best. Curve it a little bit more away from the previous glass. There you go. Too hot on your, hey, should be all right. Curve a little bit more even from the other glass. There you go. Do we see chunks? Doesn't look terrible from here yet. I don't know what's going on. Yeah, nice fingers in the chalkboard sound. Does that seem like it's probably far enough back you won't be in your way for this last guy here? Because this one is going to be almost that way. Or I could just put it back here. get far enough away. Maybe I'll put it back there. Which means maybe we'll do it like that. And that way we'll get a little better position here. I think it's still enough on camera, so we'll just leave it alone. So back that way. Okay. Last but not least, we've got composition I. 90 grams Michigan sand, 50 grams sodium carbonate, 25 calcium, 0.001 cobalt. This is a straight run soda lime with relatively high sand from Michigan and cobalt. So this should be pretty straightforward as a nice dark blue. We'll put that one right there. All right. 3i. Okay, that looks good. So next up, we'll do our instructional videos. So I think we're all done with that. Thank you for risking it all up here. Appreciate all your help for those that did various jobs. It takes a little while for all this to cool. Yeah, feel free to snap pictures. Do watch those crucibles. They're going to be bleeding a lot of heat right now. And we'll have plenty of time to look closer once it cools off. But and yeah, I'd put the fiberglass in the glass bin. It's just I've seen people get stuck by that so quickly. So when you least expect it. So we will keep the video on the table in case any more of them happen to shatter. We'll capture it. But this next piece seems like it's almost a tradition. The professor before me that had been doing this from like the 90s had this old video that's showing art glass in the 90s. It's kind of cool. So I've continued using the old school video. The glass art shop is the workshop of Dale Chihuly, which probably only means anything to you if you know art glass. But he's a really famous glass blower and has been commissioned for museums all over the world and airports and pretty fancy, ornate stuff. And so this is his team in Seattle. And there's kind of a, hipster vibe or something to this whole thing as well, but it's kind of old school. Dale Chihuly himself, he's kind of an interesting character. He's got an eye patch. I used to think it was because he got poked by hot glass, but it was actually just a car accident. It's like nothing to really make light of. And even though he's kind of an interesting character, he's really made a name for himself in hot glass. And so it's kind of cool to see what can be done with this as a medium. So we'll look at this first, and then we'll look at bottle forming equipment, which is maybe more of our wheelhouse. So let me get the sound rolling. Okay. So I think.
Studio at home in Seattle, Washington. This is where Dale's.
I don't know if I'm going to be able to get rid of that buzz for some reason.
Work is made. Tell us where we are. Okay, we're at the Boathouse. Dale Chihuly's studio at home in Seattle, Washington. This is where Dale's work is made and where we conduct most of the business that he does. This is the hot shop where we have hot glass.
We first met Joe, who was telling us a little bit about why Seattle is so good for glass blowing, and it's because its climate is not too hot, not too cold.
Our glass is 2150 degrees Fahrenheit, and that's the working temperature of the glass. In order to melt it, we put it on what's called high fire, and it goes up to 2500 degrees to melt it. So we should take a trip to the furnace.
Okay.
That's
That's a statement I never really expected to hear.
oh no,
We're going to take a trip to the furnace.
trip to the furnace.
So what are you doing now?
Well, I'm gonna gather this, what we call a little gather here, and I'll, you know, the pipe kind of heats up as we stick it in the furnace there. Wow. So we have this little device to keep ourselves from burning ourselves on the pipe. Turn, and then you kind of let it fall on center. There you go. It cools off.
Yeah.
There you go. See, natural. That's the right. Hang it down, and it'll go down.
Is the burn unit nearby?
We have a little device over there that catches us into the fire department. Kind of come out,
Yeah.
and then you lift it on out of there. Okay, up and out.
Lift. Yeah, there you go. Keep turning. Wow. Good. Keep turning. Good.
There you go. There you go. Now this is the marver. This is what we call the marver, and now you are marvering. Marvering the glass.
Marver is just heavy metal.
Yep. Very good. Oh, and this is a good shot coming up here too. With this is what we call a roller wrap.
We'll return to Foster in just a second. Oh, they're applying the red to it? Right.
Yeah. And these rollers are offset, so the bubble moves down and the color goes on it.
It's like taffy.
Hale founded it.
Oh, he did?
Yeah. He was the founder of the school.
So is he like the main glass man in Seattle?
He's about the main glass man in the world.
Really?
Yeah.
I was going to school here at the University of Washington and was taking a degree in interior architecture. So I had an interest in glass, started melting glass, and went out at blue glass out of a little kiln. And then from there I decided I wanted to be a glass blower.
What we're working on today are these wall pieces, okay? And so what you see a dark bubble on the inside?
Yeah.
That's actually an air bubble with a thin layer of color. That Bennett right there is about to drop on to the pipe. We're going to reheat it, shape it, and with my great team, we'll hopefully get it in the box.
So,
Oh,
just
baby.
stand on your way. Where should we be?
No, I don't want you to stand on. I want you to
help me a little bit here.
Martin works for me, but he also works on his own work and has his own exhibitions. And many of the glass blowers that have worked with me have gone on to develop their own careers. Some of them, like Martin's, you know, stay around and still work for me. Others go out on their own entirely. But there's some, I don't know if anybody told you, but there's something like 50 glass shops now, glass furnace studios in the Seattle area.
It's not really glass blowing, it's more like glass shaping. But there's a lot of prep work into shaping the bubble and very little blowing.
Well, glass blowing's difficult to get started because you have to have the equipment. So you've got an initial outlay of, you know, a couple $100,000 to have a small glass shop, and then to run it costs a couple $1,000 a day.
Actually, what you're gonna do is, these are wooden paddles and they're to protect me from the heat. Okay. All right. Teamwork. Hey, you guys are awesome. Oh wow, I can't believe you can even talk. Turn. Cap. Oh my gosh. Should I be up there for you? Wow. You can shoot. Yeah, shoot my chin. Stop blowing. All right, good. Level. Tip up. Right here. Don't stop on it.
This climate is conducive to glass blowing. It's not too hot. You know, the only really bad climate for glass blower is a hot one.
When you blow glass, you blow the bottom of the vessel first. And now we're going to break it off the blowpipe. Okay, cool. Glass always breaks at the coldest spot, right? So just a little drop of water here, drop of water there. Whoa, wow, there it is. Is that cool?
What you saw down there was, those techniques have been used for 2,000 years.
Squeeze it against you, get in. Good, now push down. Okay, good, hit the left paddle with one paddle. Good, man, you are on the ball. I'm just pushing down. Push harder, push harder now. Yeah. Ease into it, push harder, push. Let them open up. Good, push. All right, now when it starts to feel like it's not moving anymore, you're done. We've got as much work on that heat as we could. Now come out. Good job. Whoa! These were on fire. Full heat, Paul. All right, I'll take those. Okay. So how was that? That was good. We got about 2 heats left. Okay. What we're doing now is we're going to peel this ball open flat to make the wall piece. Here, well, yeah, it's actually there are ovens that are 900 degrees. The timing is just critical on that because you've got about, while it's heating, that all the work we were all doing comes down to that very last heat. That's where the shape is made, that's where the beauty happens, that's where the nuance, the delicacy of the whole piece. All that work is just for that one heat. And then in a few seconds, you come over here, and if your timing's off, crash, it falls on the floor. Where do you get your inspiration from?
I'm lucky in that the ideas come to me. You know, I probably don't run out of ideas. You know, sometimes you wonder if you run out of good ideas. Glass is a lot like water. You know, there's a lot of, I like water, I like glass, I like ice. There's a lot of characteristics. And it also kind of works like the ocean, makes forms like the, you know, there's some connection between all of that. So I end up blowing glass and stuff, everything. Half the stuff I make looks like it comes out of the ocean, even if you don't want it to. I like the thing. It's really, I find it conducive to thinking. And I always tell people, gee, if you had to write a book, you know, you want to go to the Caribbean to write the book, or you want to go to Ireland, which is a lot rainier than Seattle. And where are they going to write the best book? Even most people will admit it's going to probably be Ireland. Somebody is an aspiring glassblower, where do they want to go? They want to move to Seattle, because here we've got, you know, more glass activity than anywhere else. I mean, Venice has more glass factories, furnaces in Seattle, but we're second to Venice. And I think I would be proud to say that we probably have more glass artists.
So this piece is showing the annealing ovens that we're skipping that part today because we're just quenching the glass. But a lot of what they're saying there, you can triangulate that with some of the things we're seeing here. We're a lot of times getting unstable glass because of inclusions, where in that case, it's just all those shapes, they cool with tensions that are really odd because of all the contours and shapes. And so those would be very unlikely to survive without having a annealing oven. Anybody ever seen a hot glass shop like this? Yeah, UW River Falls actually does have something kind of like this. I was up at Corning, New York at the Corning Glass factory, and they make industrial glass too, but they had a hot glass shop. It wasn't to this degree. They were making like vases and small stuff like that. But this is one of the biggest scale operations that that's out there. If you look at some of the stuff he makes, I mean, the colors are just insane. And just think about the time necessary to make all those forms and then make it into some kind of a sculpture. And of course, he's got a world-known team that does all this, but you know, that's glass. It's just incredible that this is made out of this same medium. And so I'm sure he gets multi-million-dollar installations for his art. So anyway, next up is glass bottle formation. I also figured out that I think my post amp is starting to go, so I jacked up my preamp so I could turn down the post amp that's picking up 60 hertz buzz from something in the circuit inside. So anyway, so hopefully it will be a little more bearable than humming in our ears. A little loud there.
Is made of natural ingredients that are abundant. Making glass is made of natural ingredients that are abundant. Making it uses less energy than producing metal or plastic, and it can be endlessly recycled. Whether they're coloured or clear then, glass bottles and jars are always green. The recipe for glass combines several natural raw materials. The main ones are silica sand, soda ash, and limestone. Silica sand usually makes up about 45% of the batch. The soda ash helps melt the silica evenly. It makes up about 15%. A limestone content of about 10% makes the finished glass more durable. These ingredients are combined with recycled glass called cullet. The factory's equipment feeds precise amounts of the materials into a furnace. After 24 hours at 1500 degrees Celsius, a gooey liquid that's the consistency of honey is produced. The molten glass pours out of the furnace. Shears cut the flow at precise...
Just imagine what a bad day at the bottle factory would look like. If you get your robots mistimed, pieces of glass, blobs flying all over the place, and then keep your eye on the timing of the bottle forming equipment. As these blobs are flying from the furnace, this is all built in the basement of this place, a big drop. The bottle formers are making what's called a parison, which then moves into a blow mold and fills to make the final bottle shape. But the timing is so tight because time is money. They're making these as fast as possible, that there's a blob of glass already falling while this one's closing and making it, and then removes it, mold comes closed, and the next blob flies in like tenths of a second. So they've got this all trimmed down to literally as fast as possible. So
intervals to produce cylindrical globes. Each glob is the exact amount required to make up one bottle or jar. They drop to a device called the scoop. The scoop moves them to troughs that feed them to jar forming and bottle forming machines. A glob of molten glass goes into a preliminary mold. In a matter of seconds, it comes out as a miniature version of the bottle, known as a parison. Each parison then moves into a blow mold, the cavity of which is the shape of the final bottle. The equipment blows compressed air into the parison, stretching the glass outward towards the wall of the mold cavity. This process creates the final bottle shape and hollows out the inside. These are amber-coloured beer bottles. The colour is produced by adding small amounts of iron, sulphur and carbon to the glass mix. A similar manufacturing process is used to produce other types of bottles and jars. In this run, the company is making 375 millilitre wine bottles out of clear glass. This run is producing bottles also out of clear glass. This mould, though, has a special feature, a recessed insignia on one of the walls, which produces a raised insignia on the front of the bottle. After the bottles leave the forming machine, they travel through flames. Otherwise, they would cool down too quickly and crack from thermal shock. A loader now gently pushes the bottles into what's called an annealing layer. The bottles cool at a controlled rate as they move through the layer. This gradually releases the stress from the glass. As the bottles exit, they're sprayed with lubricant. This enables them to move smoothly through the rest of the inspection and packaging line. The bottles now single file to head into the automatic inspection station. As the machine spins each bottle, cameras and probes check for imperfections such as cracks or bubbles. The inspection equipment then examines the top to check dimensions and ensure the threads for the screw cap are molded correctly. Before shipping, each bottle gets a final visual inspection.
Good internship opportunity there, right?
Cullet in glass can be as high as 90%. Cullet melts at a lower temperature, so for every 10% of cullet in the mix, the factory uses up to 2.5% less energy to produce its glass. Now that is a clear incentive to recycle.
So there is, all joking aside, opportunity for internships at Cardinal Glass next week. Sometimes. I can't speak for right now, but I have had students that have worked there as just summer jobs or summer internships, and so maybe keep your ears out if you're looking for something in the area related to material science. I hear that people are pretty happy there, but more about that next week. We'll have to wait and see what they say. That gives us some perspective on the material, glass. Now, since I mentioned Cardinal Glass, let's go ahead and do this part. So you pass around the sheet here. So this is for Tuesday, section 1. So just maybe we'll start over here. Just pass that around. Make sure your name's on it. I'll walk through what you're signing off on. You're acknowledging that dangerous conditions can't exist. It's an in-process manufacturing site with an insanely large, insanely hot furnace. I've never had anybody get hurt. They're very professional at how they do this, but you're still acknowledging that. You do have to maybe go up and down a few flight, a little bit of stairs here and there around equipment. You agree to follow their rules, walk where they're supposed to. There's walkways that have little lines, and so in general, you're supposed to stay in these walkways because there's forklifts and shuttle carts and different things that kind of drive by occasionally. You have to wear proper attire, so absolutely no open-toed shoes. You have to have full shoes. If you got steel toes, not a bad idea to wear them for factory tours. But no shorts. I have seen where they'll ask you to go back and change. They don't let people in shorts. It's rigidly enforced, and so do follow that. Jeans are great. Steel toes. They reserve the right to throw you out. This one's interesting. Tobacco products and aluminum cans. You might not see the connection. They're not really directly connected, but they're a non-smoking campus just like us. And the aluminum can issue is if an aluminum can falls into their return conveyor system accidentally somehow and ends up in the furnace, it messes up their production for about 2 weeks because the aluminum melts, and wherever that concentration of aluminum is, it makes a rigid spot that cracks in the glass. And so they make 12 feet of glass, 12 feet wide, 20 miles long is their full day of production. It's about 20 miles of glass a day. And when they set up their furnace, it runs for 10 to 15 years without shutting down. So when you're opening Christmas presents, someone's making glass. When there's a blizzard outside, someone's making glass. You can't shut off the furnace. It's just too big and expensive. So whenever you do shut it down, it's only for rebuilding and rebricking the furnace. But then anyway, aluminum cans, so no aluminum water bottles, no cans. Just observe that, and they'll talk about it too. And so you're essentially just saying that you're acknowledging all this warning, and you'll abide by the safety instructions from the folks at Cardinal Glass. So that's what you're signing. Now, as far as where is Cardinal Glass, this sequence always makes me feel like I'm prepping people for a bombing run. It's like, here's a map of the target, folks. This is Menominee, as you know. And so we are down here. So you essentially just make your way up to 29, curve that around past Culver's, out past the hospital, and towards Eau Claire. And then right here, some of you know what this is. This is the police station. Right there. You turn on Stocky or Stokey, however you pronounce it, Stocky Parkway, right by the courthouse police building, and drive about a mile north, past 3M, over the overpass, and at this point, you'll be overwhelmed with excitement because here's Cardinal Glass, and you'll want to turn on this frontage road, and you'll end up at the back loading dock, which is the wrong place. So do not turn here. This is bad because you end up at the wrong place. You'll want to go over the railroad tracks, and then turn here. Your visuals are, you must drive between the smokestack and the water tower. If you're doing that, you know you're in the right place. And you can park anywhere in this lot right here. The receiving area is right here. So you'll just walk towards this angle in the building, and there'll be a kind of a waiting area. They usually have this little banner, "Welcome UW Stout." It's a screen. Come on. So you'll go there, and we'll be meeting at 9:30. So it's a 2-hour tour and a 3-hour lab, so that way you've got time for logistics and driving and whatever else to get back for your next class. And you can see it's a pretty big site. So this is the furnace. And then this is the annealing leer. And then this is all cutting, packaging, and storage. It's enormous. I mean, just racks of glass everywhere. Obviously, watch what you touch. They are careful to warn, but sometimes there'll be these felt top tables, and people have a habit of wanting to kind of lean on them. They don't want you touching that because everywhere you look, there's places where they've been breaking and snapping glass, and there's these little flakes of glass everywhere. And so in general, just keep your hands in your pockets. It's also loud, so they give us headsets so we can hear what they're telling us about the process. But it's one of my favorites in terms of industrial site tours because it's all about glass. It's all about one product. So that's unique. Another unique piece about this is the sand that is used for Cardinal glass is mined right here. The sand mine that is just east of town is the source for the glass that's made a mile north. And so if you were to go a little bit further past, you'd see that. And then interestingly, after being made, this glass gets shipped. It used to get shipped to Toma for a finishing plant, and then some of it gets shipped right back to Anderson Windows and put into window units. And so the cool thing about that is it makes this triangle. The sand gets mined here, made into glass, finished somewhere else. They put a coating on it at a different Cardinal site, but then it comes back a half mile from where it started and is put into window units and then shipped all over the country, or maybe all over the world. So that's kind of an interesting footnote. So, all right, so questions about that? Can't find a ride, post on the board, hey, I need a ride. Or if you have extra seats in your car, please post that so that we can all get there safely, since Stout doesn't provide transportation. Oh, that was the giant yellow one. What in the world? I don't even think I measured that one, did I?
It didn't look like it was going to break.
I know. Way to go, Dr. Ray. You know, you just take certain things for granted. I'll clean all this up, put it in a beaker here momentarily, but I wanted to... That one really shattered. There's like shrapnel all over the place. Crunch, crunch, crunch. I want to tell you a little bit about internal stress. You're like, Dr. Ray, you don't need to tell us anything about internal stress. Listening to you an hour is internal stress, okay? So, yeah, I get it. But glass also has internal stress. Okay, done with the little shuffle dance here. So this little light table here will allow us to see internal stress. I'm hearing unhappy sounds over here. So when this glass cracks, it cracks along stress lines. What are these stress lines? Well, as the glass cools, and so underneath this paper here, I've got a bunch of other samples from the past in case you're curious to see what some previous groups got. Let's take this one for example. So internally, because this was poured from a melt, as it cools, it's shrinking, and so that compresses some bonds and stretches some other bonds, and it causes there to be a preferential orientation along certain directions of the polar covalent bonds and ionic bonds in the glass. Well, anything that's not isotropic or equal in all directions causes light to interact along those bond axes a little bit differently than it otherwise would, and it causes the light to become polarized. Has anybody ever studied polarizing film before? So what this is is it's a preferentially oriented polymer films can do this. There's also certain metallic layers that can be added to films. But a Polaroid film just looks like a sunglasses in this direction with one, but once there's two, notice I can turn on and off the light that goes through because it only lets light in a particular direction, vertical, go through. So if this one's vertically oriented and this one's horizontally oriented, no light goes through anymore. This is the nature of polarized light, polarizing light. So if I put these in a crossed configuration, and then I put a piece of glass in between, then what you see is the polarization effect of the bonds in the glass is all you can see that remains. And it looks like a rainbow. Taste the rainbow. And if you look at the pattern, it's a semi-quantitative way to analyze internal stress. The way it's semi-quantitative is the tighter the color bands, the higher the stress field. The more spread out the color bands are, the lower the stress field. And so you'll see both. Like in this piece of glass, there's wider bands in the area, I think, where it was poured and fired more, but then it tightens up around the rim. And so that's where you usually get cracking. It will start on one of those high pressure zones and then propagate through the whole piece of glass. You can read a lot more about, or watch a lot more about that with Smarter Everyday's video. He even acts it out. It's kind of cheesy, but it's kind of funny too. You might know the guy I'm talking about, but that channel is pretty well respected. So it's not burning my hand, so I'm going to put your glass on this light table, and then you can grab a ruler and measure the ones that survived, and I will put the remaining ones in beakers so you can analyze the color or observe the color. You should still wear your safety goggles because these things still shatter over here on the light table. So you really only have 5? It's been a rough day, folks. But anyway, you can look at it with and without the cross polarizers, but you can go ahead and start making your observations, and I'll try to safe this area up here. That's the show, folks. So go ahead and make your observations.
What letters were the ones that shattered?
Stay tuned on that. We'll have to make a row in the beakers here.
So the Crystal Lab is due today, and it's just like the same way we submitted the other one?
Yes, the Crystal Lab is due tonight, and it'd be cover sheet and cover report and questions and data and questions.
Data and questions.
The way this breaks into little tiny pieces might remind you of safety glass. That's because it is like safety glass. Safety glass is pre-stressed along certain axes that make it shatter into a little checkerboard pattern. These are random, but they still break into little chunks because of that stress field.
Were those the 2 middle ones? shattered?
Uh,
Because then I think it's E and F.
well, possibly. I'll try to get a final answer on that here in just a moment. So I'm right behind you here, so.
Oh, they're fine. Sorry.
Yeah, you can measure them now. The rulers are over there. So we got 3F was the lime green one. And then this one. Yeah, 3E.
Didn't think ours was on
Yeah, E, it looked all stable and nice. Yeah, I'm kind of surprised that one finally went, but we can get them lined up here on paper so you can see the colors here. So these are the ones that Baroque, and we can pull the paper off of these if you just wanted to see some of the different colors. This isn't an exhaustive list, but it's a lot of the ones from recent years.
This one's 3G. Okay. This one is 3I.
Mm-hmm. So did everybody get a chance to sign Cardinal glass sheet here? Make sure you do. And definitely wear your goggles when you're up there by that glass. It still shatters when you least expect it, and little flakes of glass in the eye have a way of ruining your day. So recommend wearing those constantly over there.
What did I want? It was in the like lab thing. It should have been the links. Yeah, it should be like data sheets only or something like that.
Also, your batteries.
Yes. Yeah. Yeah.
So I'm gonna go scan these batch records, and then I'll get those back to you. So I'll be back in just a couple of minutes, and you can get your record.
Yeah, I've got like all of them except for E.
Three E's.
F.
F is 56
They're all
under
wrong,
E.
really, except for what we got. Trying to find out, and I want to. Follow it. That E. The color is, yeah. It's like a gold yellow. Nobody has it there. No.
Yeah,
Think about taking one. Or what? Which ones do you need? Are you good?
I'm good. Okay.
Yeah.
You did a lot of it.
We didn't get it.
Correct.
Yes. What about it? Oh, yeah.
All right, we've got these are ready for you to pick up now. Your batch records, we'll just set them up front center here.
Yeah. Oh. Well, I'm still gonna take it.
I'm sure you always heard you can melt sand to make glass. Now, you've seen it happen. You've made it happen. So certainly not today. They do need some time to stabilize. I've had them crack up to a year later. So I was in my office one summer. I was doing something. Happened to be in my office, and there was this cabinet that I had a bag of these things in my office. So I need to work out an healing protocol, and then we could just do a slow heat, pause, and then cool down, and then they'd be fine forever. So let me look into it, because obviously I've got a lot of decent glass. So I'd feel a little better about it if it was annealed, because then it would shatter your copy or something like that. So let me work out an healing protocol. They'll be hanging out here at the front of the lab for the rest of the summer. You know, it must be, you know. So iron is what gives window panes a little bit of green color if you look from the side. So typically it's green. You ever notice how glass, you look at the edge, it's a little bit green. If you ever install windows, get new panes of glass, it's kind of noticeable from the edge. But that's iron. But iron also is responsible for like the brown color, brown bottles, brown glass. But in this case, it looks like he's adding that borax. He's tilted it to being green. I can show you what it typically looks like. So iron usually does something like this, or this, or this. These are all yours definitely tilted over brown. See, that's a frequent. That's really typical for what we've seen. The borax clearly is interacting with the iron. And this one's like that's definitely brown. But it's not out of the question for what iron can do, since brown, all brown bottles you've ever encountered are probably iron in color. It's just kind of cool that it's kind of expected. This is the first year we've done straight borax. Boron oxide. The borax is a little bit more of it's still a raw mineral. I mean, it's been crystallized, but it's not as processed as boron oxide. So clearly has something else in there that's interacting with the iron.
The ones that shatter.
Like I said, this video from today will also be on the playlist. That way you can review what happens. It's also kind of fun to find the moment things shatter and like look at how the pattern, what changed. So we'll put that on our normal playlist. Yeah. Yes, it's a former and it's also a stabilizer because it makes ions that can bond 3 times aluminum oxide. So it's kind of in that two camps. It's still a glass former, but it's also a stabilizer. Or it's too tight and it actually can destabilize because it pulls too much in. It makes too much tension. So I can see it being in both.
Do you want this? What is it? Oh, this is that all on the spreadsheet. Yeah. You want it? Yeah, I'll take it.
Oh, really? It's all the great stuff. I mean, that's not a big deal, though.
classroom type class into jobs. Other things you're hoping to learn is to learn the different ways that different parts of our company interact. So what's nice about a job is, let's say you're
Table's done.
you can see how purchasing and warehouse influences availability of stuff, and then looks for on-time delivery, marketing, and how they all might talk to you about what your needs are, when it's going to be done. So you
Yeah.
see this kind of like, you see how it all fits. And then administration, how, so that's a cool part. What part of this do you want to from technical sales to manufacturing, supporting all the way through, so there's that. And so if you just kind of brainstorm and like, you're also learning things about synergies between
Next month.
Yeah.
Suppliers.
supplier company. Yeah.
Yeah, I see that.
Oh. Okay. What
I
I
have
think
it in there, I think
exactly what they do, so we manufacture.
you got it for that. The concentrations are changed. That's on like that's on the spreadsheet I did.
Yeah.
So after firing, we have to take.
So,
You have to take whatever.
you know, say that your objective is seeing how
This one makes sense because it's such a
how
amount.
far more good, you're still doing the part of it. But then the drop, so if you use someone else teaching it, like, so you finish so customer relations and just that workflow. So is this not go on? Yeah, I'd say that from that perspective, being one part of the thing. Thank you. Yeah.
Yep. And that's 15 grand. So each time it's 15 grand. So that's
I mean, ideally, you put both. I mean, like in parentheses. I'm not going to be like require a particular chemical formula. I'd like you to be aware of what those are. And so,
and the finance is just down.
yeah. So I'd say that the best of both worlds would be if you put in the ingredient and then just in parentheses the chemical formula. That would be perfect. Because then you know common names as well as the formula. You can see how it all fits. So that's my best. But it's kind of I'm here to stipulate. Yeah.
I'll do what I can.
Yeah. I'd let them sit a little bit longer, but yeah, eventually you do that. I was talking to somebody else about annealing the glass, and so I'd say put that in a beaker, and then you can eventually, but maybe not today, because we want to let it completely season and finish cracking and everything. But yeah, you can label a beaker and it's fine. Yeah. That actually.
Do you see what I'm taking? Last class, well, there's no, there was, and then I went out to it. Upload.
got in the habit of doing everything on Dropbox, and students seem to like that because then they don't have to print out the cover report. And so if you just put it all into one document, then it's just a file submission. It just makes it easier to read. So I suggest doing it that way. I also, for a while, I had paper and online, and it got confusing. But, so we made it all online. So just submit it to Dropbox. Yeah, scan it and either PDF directly or import that into the document. As long as it's legible.
So, do I not need the number that you sent?
No. So this is the moment that green one shatters here. You can slow it down a little bit. Yeah, you can control the lights. Which one's? See how fast it happens. So right there is, and you can see there's nothing occurring. It's all internal stress. It's springs that just break it open. So right there. And then we have that yellow one.
And then do I change like the new or something? Cool.
Look at that. Yeah, that's a big one. There's a lot of energy.
Yeah. That's another group. That's tight.
I can see that you're
Flying, that's
plug fail. Oh, because you're doing.
Dr. Ray, we didn't have lithium, like no one used lithium as a flux, right? It was either sodium or potassium.
We didn't even use potassium. So I mentioned that those are so
Oh, right.
those have created so many problems for me that I kind of swore off of them. I mean, it's nice to see some examples of it, but the one destroys the furnace and the other one always cracks. So sodium is like that nice middle of the road. Lithium also has some toxicity, vapor hazard type stuff that's kind of overlooked. So sodium is one I like, but I have pictures there for you to compare with in the lab. There's a few representative glass discs for you to cite off of to make a conclusion.
Oh, Dr. Ray,
Yeah.
your spreadsheet, 3D, doesn't have like the colors that they used to do, the diamonds, whatever they used to.
It doesn't?
For. So we can figure out there's something what we use. Like, yeah,
Well, we can just go ahead and add it in for them. So 3B. So 0.8 copper oxide and 2 grams for iron oxide. That should solve that problem. I thought everybody had their ingredients there. I must have overlooked that. Does that fix it?
Yep.
All right.
Thank you.
Yep.
For the table. How do you get the?
You can use the net number. If they just have one, then you do like 0.699 divided by this odd number, like 128.
Yeah.
And that gives you a really small percent.
I mean, it's already programmed in there. You don't actually have to do any more calculations. So I was just showing you how it calculates. So it takes the oxide mass times the percent iron or the percent metal, and then divides it by the fired batch weight. And those are the numbers that are already in that far right component of the table. That's already in percents, and so they're small decimal percentages. So it's just as simple as just transposing that directly.
Okay. Yeah, so the one's all the way to the right is all these.
Yeah, that little table that's in yellow, that one's already calculated. to get a picture of all the different colors at once, I aligned the crucibles here, and it makes a fairly nice picture. It's just A, B, C, D, E, F, and then 2 rows there right down. You can clearly see all the palette that we created. This is more of a glaze at that point on the ceramic, but kind of cool.
Only mistake was the aluminum. Is that what you think it was?
So if you look at these little blobs in here, you can crack into them. They're still powder. So I'm thinking this is aluminum. Now there's an ingredient called zirconium that is even worse at doing this.
And it probably just didn't get mixed.
It probably didn't get mixed, and so that blob didn't have the flux right next to it. And so I think that it must have been pouring out as little clumps, and those clumps didn't get mixed with the flux. And so I'm stuck with that. It's probably the root cause of a lot of this.
Yeah.
So it's like the recommendation would probably be you have to at least take the alumina and like if we milled that with borax, we'd probably be perfect. Because then there'd always be microscopic alumina particle next to something that's going to melt. Where this made
Like
this
a pre-mix and
Yeah.
then mix all.
this made like one of those. You know how the Romans used to get in those formations where they had shields out and they made this like little turtle.
Yeah.
That's what it does, and so it shields against the melt and it can't get into the interior of that particle because it's not mixed. So we had a clump of alumina. That's the theory I go with.
So would you say that adding borax would be very recommended?
The
'Cause
borax.
that's what else we did. I don't think we put
No,
borax.
we did not.
just did.
Well, the borax seems to counteract some of that alumina,
Right.
but I think if it had been milled completely, it probably wouldn't have had this issue anyway. But for some of the ones that did still turn out, it seems like if they had high borax, we could counteract this by being so easy to melt, it still chewed through it. But yeah, I've never had this number of little powder inclusions before, so something must be up with that particular cup of alumina that we used. It might have already been like drawn some moisture and got a little bit clumped up that it hadn't been in the past. So we're a victim of circumstances.
Yeah.
Alright, never know.
Yeah. See you later.
I mean, we can put it in. It says how to visualize. Would that work?
Yeah, you can just take a picture. It shows it perfectly. Some of these are kind of interesting. This one has a really nice symmetric stress pattern right in the middle, where these are a little more irregular. But this one's almost like a perfect bullseye. So that must have been a really nice symmetric pour. Where some of these like went off to the side. But you can actually tell quite a bit. And I didn't talk to the class too much about that just not yet. But you can also do the plastic parts, and you can see where it was injected. And you can tell that was the gate, and then it went into the mold. So this technique with cross polarizers, you can actually learn a lot about the interior of the material. It's one of my favorite ways to visualize